Now we will look at the aerobic technologies, which can be used as standalone systems or to polish the effluent of anaerobic units. Aerobic systems are biological systems which rely on the action of bacteria needing oxygen to live, like us. Thus, in all of them, oxygen provision is a key aspect. Without sufficient oxygen, the environment becomes anaerobic, which leads to processes such as described in the last module. Some aerobic technologies try to imitate nature, such as the waste stabilization ponds or the constructed wetlands. Some others are more engineered, such as the trickling wave filter or the activated sludge. Let's start with the waste stabilization ponds or lagoons. It is a system that consists in a succession of ponds with different functions. First, one anaerobic pond, then one or two facultative ponds, and finally one or two maturation ponds. Let's look in more detail at the differences between the three types of ponds. The anaerobic pond is the deepest, with a depth of 2 to 5 meters and also the smallest. It is highly loaded because it receives the raw wastewater. The anaerobic pond has a hydraulic retention time from 1 to 3 days, and its main function is sedimentation and anaerobic stabilization of sludge, thus settling. The facultative pond or facultative ponds, if there are several, are shallower, usually less than 1.5 meters, but large. The idea here is to maximize the oxygen supply, either through algae, wind, or artificial aeration. The hydraulic retention time there is longer, from 10 to 20 days. Here, the main function is the aerobic degradation of suspended and dissolved matter, thus degradation. Finally, the maturation ponds are even shallower, usually less than 1 meter, but large. The hydraulic retention time is about 10 days. Here, the main function is the final sedimentation of suspended solids, the bacterial mass, and pathogens, thus polishing. Waste stabilization ponds can treat high-strength wastewater to a high-quality effluent. They are generally reliable and good functioning and inexpensive compared to other centralized options. However, they require a lot of space and may generate bad odors, especially the anaerobic pond if poorly designed. It requires expert design and supervision, especially to avoid short-circuiting, in which case the effluent goes from the inlet to the outlet without mixing properly. That's not staying through the intended retention time. Besides, if they work at best in warm climates, waste stabilization ponds are not always appropriate for colder climates. This picture shows large waste stabilization ponds for the city of Cuenca in Ecuador. A way to increase the performance of waste stabilization ponds is to provide artificial aeration, which is done in Cuenca in the first pond, upstream of this picture. It is also a good way to upgrade the ponds when they reach design capacity, as spatial extension is not always easy. In aerated ponds, mechanical aerators provide oxygen and keep the aerobic organism suspended to achieve a high rate of organic degradation. Increased mixing and aeration means that the ponds can be deeper and tolerate much higher organic loads than a maturation pond. The depth may be from 2 to 5 meters and the retention time from 3 to 20 days. In some cases, it can even replace the anaerobic pond, thus avoiding the bad odors that anaerobic ponds may generate. The downside of it is that aeration implies a high energy consumption and thus costs and requires a constant source of electricity. Interruption of electricity service may cause the pond to turn anaerobic, thus changing completely the inner biological processes. We will now have a look at another family of treatment technologies, the constructed wetlands. Constructed wetlands aim to replicate the naturally occurring processes of a natural wetland, marsh, or swamp. We distinguish three types: the free-water surface constructed wetland, the horizontal subsurface flow constructed wetland, and the vertical flow constructed wetland. Let's start with the free-water surface constructed wetland. In that case, the water slowly flows through the wetland, particles settle and pathogens are eliminated through the combined action of sun, settling, adsorption, and predation from higher organisms. The organisms and plants utilize the nutrients. This type of constructed wetland is commonly used as a polishing step after secondary or tertiary treatment processes. It is only appropriate for low-strength wastewater. This is a really important fact. The depth of the water is 10 to 45 centimeters above ground level. Wastewater needs to be well distributed at the inlet. Good operation and maintenance is needed for it not to turn into a mosquito breeding area and to avoid short-circuiting. Let's look now at the horizontal subsurface flow constructed wetland. Its performance regarding reduction of BOD, suspended solids, and pathogens is higher than in the free-water surface constructed wetland, and it does not have the mosquito problem as the water flows only under the surface, as its name indicates. As in the previous technology, the good distribution of the influent at the inlet is very important. The gravel bed is between 50 centimeters and 1 meter deep, and the water level is maintained at 5 to 15 centimeters below the surface. As wastewater flows horizontally through the basin, the filter material filters out particles. It acts both as a filter and as a fixed surface upon which bacteria can attach, forming large biofilms. The plant roots play an important role in maintaining permeability in the filter. It is very important to have a good primary treatment before the wetland. Otherwise, the risk of clogging will be very high. Expert follow-up is necessary to manage the plants, especially the startup periods. As a final remark, we have to mention that the wetlands need a lot of space, generally a surface of about 5 to 10 square meters per person equivalent. This picture illustrates the last type of constructed wetland, the vertical flow constructed wetland, which is of course difficult to differentiate from outside. This is the most sophisticated and performant type of wetland. By injecting the wastewater from above the whole surface, the distribution is greatly improved. The water flows down and is collected by a drainage system. The important difference between a vertical and a horizontal wetland is not simply the direction of the flow path, but rather the aerobic conditions. The wastewater is applied intermittently, 4 to 10 times a day. Thus, the filter goes through stages of being saturated and unsaturated, and accordingly, different phases of aerobic and anaerobic conditions. With this regime, there is less clogging risk than in a horizontal subsurface flow wetland. Other than that, the treatment processes are the same as in the horizontal flow wetland. Because of the mechanical dosing system, this technology is most appropriate where trained maintenance staff, constant power supply, and spare parts are available. Constructed wetlands can reach a good performance with processes close to nature. However, one has to be aware of the risk of clogging and the management of the plants, especially the startup and maintenance, and beware high ammonia levels, which may prevent the plants to grow properly. In all cases, a good primary treatment is crucial. Before finishing this module, we will still look at two high-end technologies which we may call conventional, the trickling filter and the activated sludge. These systems are very performant in developed countries, but imply high capital costs, operation and maintenance by skilled personnel, and a constant source of energy. The trickling filter is a fixed-bed biological reactor that operates mostly under aerobic conditions. After primary treatment, wastewater is continuously trickled or sprayed through the filter, for example, through a rotating sprinkler. Organics are degraded by the biofilm covering the filter material. The filter is usually from 1 to 2.5 meters high, but some filters may reach a height up to 12 meters. Adequate airflow is important to ensure sufficient treatment performance and prevent odors. The air can circulate vertically through the filter. The advantage of a trickling filter over the technologies presented before is the small land requirement. However, flies and odors are often problematic. The activated sludge system is the best known and most widespread in Western countries, under different forms, such as sequencing bioreactor, oxidation ditches, moving beds, or membrane bioreactors. It makes use of highly concentrated microorganisms to degrade organics and remove nutrients, leading to a high-quality effluent. To maintain aerobic conditions and to keep the activated sludge suspended, a continuous and well-timed supply of oxygen is required. Aeration and mixing can be provided by pumping air or oxygen into the tank or by surface aerators. Agglomerations of sludge particles, called flocks, form in the aerated tank and are removed in a settler, called in that case secondary clarifier. We are now at the end of this module on aerobic treatment technologies. We saw very different technologies that can all perform well but have different requirements. To sum up, we can say that the main decision factors are the availability of space, financial resources, skills, and electricity.